The next unit that we get into deals with two concepts called momentum and impulse. I like to do this section after we just completed the forces section because it really does deal with a lot of the same concepts, just looking at them a little bit differently. In the last chapter, we were kind of looking at the relationship between three things, and those three things were force, and more specifically, net force, mass, and acceleration. And we talked about Newton's first law and about things staying the same, that if the net force is equal to zero, that object will continue to do what it was doing, that whole concept of inertia. And Newton's second law, where we dealt with the relationship between force, mass, and acceleration, or net force, mass, and acceleration, and how if we changed one, another one might change, and all that stuff. We're going to continue looking at the relationship between these three things, but we're actually going to throw in a fourth factor. This, remember from an earlier section, actually depends on two things. The definition of our acceleration is equal to delta v over delta t. So this actually looks at the rate at which the velocity is changing, but when we talk about Newton's second law, it doesn't really tell you exactly how much the velocity changes. It tells you how quickly it's changing, but not exactly how much. And that gets us into the impulse momentum equation. Where does it all come from? It starts with Newton's second law. Here we are, right? Sigma F is equal to m times a. And we looked in the last chapter about the relationships between these things, that if net force increases, then acceleration increases for a direct relationship, that if mass increases, the acceleration or the rate of change of velocity decreases, inverse relationship. Those are all things we talked about in the last chapter. But in this chapter, we want to take it and throw in another factor. So, taking what we just talked about, acceleration, we just discussed, is actually a relationship between two things. The change in velocity over the time during which that change occurs. So, if I take this expression for acceleration, sub it into this equation, so m delta v over delta t, do a little algebra, I end up with this equation. Sigma f times delta t is equal to m times delta v. We refer to this expression as the impulse momentum equation. There it is. Sigma f is times delta t is equal to m times delta v. This relationship sort of shows us the same thing that the previous relationship, or Newton's second law, was showing us, but now it adds in a little bit more detail, one more factor. It still deals with mass, but now we throw in that time factor. And that's the part during this, oh, not that one, sorry, my bad. We now include that time factor and see how it affects the resulting change in motion, or the change in velocity. In the last chapter, we just talked about a big force causes a big acceleration, and that's true, that during the time over which that force acts, the rate of change of velocity is very large. During the time during which that force acts, the velocity changes at a fast rate. But if that force only acts for a very short amount of time, the acceleration may be large during that time, but the actual change in the motion, the delta v, the change in velocity, may not be very big at all. So that's the one thing that we're going to start looking at in this section is, okay, if we apply a force for a certain amount of time, how much change do we actually cause? How much change in the motion of that object, or the velocity of that object, do we actually end up with? So the impulse momentum equation depends on two things, or it relates two things. The first, well, those three things. The first thing that it brings in is this thing called impulse. Notice, impulse causes a change in the object's momentum. Notice, change in the object's momentum is in capitals, it's bold, it's italicized, and now, through the miracle of modern technology, it is also highlighted. Okay? Impulse causes a change in the object's momentum. If we're talking about a change, hopefully you make that conclusion that, okay, things that change have to be the responsibility of a net force, right? An unbalanced force is what causes things to change. We discussed that conceptually a lot in the last chapter, and we looked at the difference between an object that experiences a net force and experiences acceleration and an object that's in equilibrium, where it may experience multiple forces, but those forces are balanced and there is no net force, so there is no change in the motion of that object. So impulse causes a change in the object's momentum. Net force applied for a certain amount of time. So now we take into account, okay, how hard are we pushing or pulling, the net force, and then how long will we be pushing or pulling? Because that is going to have an effect on how much does the motion of that object actually change. The other side of that equation is the momentum side. We define momentum as the product of the mass times the velocity. That we would refer to as the instantaneous momentum. What is the momentum of that object right now? As far as a definition goes, you'll see at the top of the screen, it says it's a measure of an object's motion. I don't know, that definition is kind of good, I guess, but it's kind of weird in the fact that, what does that mean, an object's motion? Some people like to describe it as inertia in motion, but inertia deals with things in motion already. It kind of takes into account the idea of, okay, how hard is it going to be to change this object in the idea that it's moving and it has mass. So it takes into account both of those factors. Whereas the momentum is equal to the product of the mass and the velocity, m times v. And momentum is a vector quantity, so it has direction. A car traveling at 35 miles per hour in this direction, that exact same identical car traveling 35 miles per hour in the other direction has a different momentum because the directions are different. So the impulse momentum equation relates how do we deal with, or what kind of results do we end up with if we apply a force for a certain amount of time to an object with a certain mass. How much change are we actually getting out of it? And that's really what we're going to be looking at over the next couple of weeks. Important thing to remember. The change in momentum is equal to the impulse applied to the object. So notice, once again, change. Capitals, oh, it's not capitals, it's bold, it's underlined, and now it's highlighted. Okay? Impulse is equal to the change in the momentum of the object. If we look at the right-hand side of this equation, which we said was the momentum side, notice that momentum, I defined it before as P is equal to m times v. But the right-hand side of this equation looks like P is equal to m times delta v. There is a change in the motion of the object. That's the delta v part, the change in velocity. So we can expand that side of the equation to look like this, v final minus v initial. And then this becomes, sorry, I should have done this, the change in momentum, delta p, because you have to figure out, okay, what was the momentum at the beginning of this situation, m times v initial, and then now what's the momentum, m times v final, and take the difference between them. So the impulse, the net force applied for a certain amount of time, causes a change in the momentum, a change in the velocity. Velocity deals, or velocity, or momentum depends on velocity. So if there's a changing velocity, there is a changing momentum. That's it as far as concepts are concerned. Let's take a look at the application of a couple of those concepts. I'll show you a couple here in the video. We'll talk about a lot more in class tomorrow. Here's a picture of two eggs being dropped. Let's assume those eggs are being dropped from the same height. Knowing what you know about gravity and the effect that gravity causes, you should be able to tell me that if I drop two eggs from the same height, regardless of what their mass is, they should be traveling the same speed when they get to the ground, or just before they get to the ground. If that's the case, if we drop these two eggs, and let's say these eggs, for the sake of argument, have the same mass, because that'll just make our lives a little easier. If we drop these two eggs from the same height, and they're traveling at the same speed when they get to, I don't know, say like, stand by. If they're traveling the same speed when they get to, like, say, this point, how come one egg breaks, the one on the left, and the other egg on the right doesn't? Obviously, you could say, well, that one hits the plate and this one hits the pillow. But there's something about those two surfaces and how the forces and the times interact that results in one situation and another situation. If we take a look at the impulse momentum equation, right? Sigma F times delta T is equal to m times delta V. In both cases, the change in velocity is going to be the same, like we just discussed. If I drop it from the same height, by the time those two eggs reach this point, they will be traveling the same speed. And in both cases, they end up stopped. So if we looked at delta V, let's not use that color. If we looked at delta V for both of these situations, V final minus V initial, the V final for both of them at the end of this situation is 0. So we're talking about 0 minus some initial velocity. We've already established from the fact that we know what gravity does, that the initial velocity when it reaches a certain point, which would be like the beginning of the situation when we're looking at these objects, that velocity is the same. So the delta V is exactly the same in this case. If that's the case, if you look at the right-hand side of this equation, I told you to assume the eggs have the same mass, so they have the same mass, and then they have the same change in velocity. The right-hand side of this equation must be the same. Those eggs experience the same change in momentum. If we look back, though, remember that change in momentum is caused by impulse. But impulse has two factors, a force factor and a time factor. Either one of them, we can mess with either one of them and have the resulting change in motion be the same. When we experience a same change in momentum, as we do in the case of this egg, force and time will have an inverse relationship. In the case of the pillow, that egg hits the surface of the pillow and then the pillow cushions with it. The whole time that pillow is cushioning, it's applying a force to the egg. So we're increasing the time over which that force is being applied. If time gets bigger, the force that needs to be applied would get smaller, an inverse relationship. On the other hand, in the case of the plate, that plate applies a force for a very short amount of time, just the instant which that egg is hitting the plate. It has to accomplish the same change in motion, the same slowing down of that egg and bringing it to a stop, but over a much shorter amount of time. So in the case of this one, in case of the picture on the right with the egg and the pillow, time is increasing. Let's go this color. Time is increasing, and that means that there doesn't have to be as much force. But in the case of this picture here, the time is very, very short. So it has to apply a greater force to accomplish the same change in motion, the same change in momentum that the pillow does, but in a shorter amount of time. So you need more force. That force is too big for the shell of the egg, and it causes the egg to break. So when we see the change in momentum being the same, regardless of what's going to happen, how it happens, we can mess around with the force and the time to cause the same change in momentum in a different amount of time, requiring a different force. We can do the same thing with a big force over a short time as we can with a small force over a larger time. The next situation is probably something that most of you are familiar with. If you've ever played any kind of sport, any sport that requires throwing, kicking, hitting, any of those things, jumping, there's an important concept that we refer to as follow-through, right? When you are hitting a golf ball, as in the picture here, or hitting a tennis ball, or hitting a baseball, or throwing a baseball, or shooting a basketball with your hand, you don't just stop your club, racket, bat, foot, hand when that object leaves your hand. There's that idea of follow-through, right? The actual point of contact in this picture occurs right somewhere here-ish, okay? But that's not where that club stops. Notice he follows through all the way, going through and making sure that that club goes all the way past the point of contact and allows for the whole idea of impulse momentum to do its thing. Going back to, once again, our impulse momentum equation, sigma F is equal to sigma F times delta T is equal to M times delta V. In the case of this golf ball, we're trying to make delta V as large as possible, right? We're trying to increase the change in the velocity. We're trying to hit it as far as we can. That's not always the case, but in this case it is. So if we're trying to make delta V as big as possible, here, the other side, delta V, causes a change in the momentum. Remember that change in momentum is caused by impulse. And impulse deals with two things. Impulse is a result of two things: the net force applied to that object and the time over which that object acts. By swinging the club hard, that takes care of making sigma F as big as we can. But in the follow-through, what you're doing there is that you're actually increasing the time during which that club and the ball are in contact with one another, or the club and the racket, or the club and the bat, or your foot and the ball, or your hand and the ball, whatever it is. By following through, you're applying that force for a longer amount of time. So you swing the club hard and that makes the force big. You follow through and that increases the time. If you make both sides of the left, or both terms of the left-hand side of this equation as big as possible, the right-hand side has to be as big as possible as well. The mass of the golf ball, that can't change. So that stays constant. So the only thing that can change over on the right-hand side is the delta V. Follow-through increases the time that the club and the ball are in contact. You're making force large, you're making time large. That causes a greater change in a greater impulse, which causes a greater change in momentum, which, if you keep the mass constant, means that the velocity has to increase as well. Those are the big issues. That's the beginning part of the relationship between impulse and momentum. And once again, we said that it all comes back, let's put this up again, it all comes back to this equation, the impulse momentum equation, which relates the force. Now we're including a time factor and seeing how what change in motion that ultimately causes. We'll talk about some more situations in class tomorrow and start talking about some details, applications of this. We'll see you then.